Okay, so hello everyone, and welcome to the week 8 material for the material selection and design. So we will start with the topic number 7, which is going to be resources, reserves, and the material production 2. That's completing the part 1 we did last week. So we start first with, once again, to review for the most consumed materials that we have in general. So we said that in 2022, the world's annual production of engineering materials was the highest amount was for the concrete. And then we had the steel, the glass, aluminum, and the copper. These are the top 5 materials that we have. Now we get back once again to the steel production as the first part. In this slide, we're supposed to have a video to be played, but I'm going to pass this one because this may cause the muting of our video. So in general, I'm going to remove the next slide and I will make the recording later. So we start first with the steel production. In general, you know that the steel actually, the iron actually found as an ore, and then the ore is going to be treated, melted, and then we are going to have the iron, and then the iron can be made developed to a steel, and the steel later can also be treated to be a stainless steel. All these materials can be formed, shaped to a different products like what we have in this photo. So again, as I told you in the next video, then I will go to the steel production process. So the steel is an alloy of the iron and the carbon. So when the carbon can be mined as a coal, the iron exists and as an oxide ore, such as the freon oxide or the freon trioxide. So, or as a silicate, such as what we have in the case of the taconite. In general, the general process for making the steel will involve firstly extracting, processing, and distributing of the ore itself, and then reducing the ore to an iron, and this will be done by the iron making, and then refining the iron to a steel, and this will be the steel making process, then finishing into a useful geometry, which is going to be the different uh, forming and shaping processes. So you can see in these two diagrams how the iron making start, how the steel making, and how the finishing is done. And the concept is going to be very easy. We are going to have the iron or the limestone, again, to put them in the sinter plant, and we are going to add some carbon to it by using the cook oven, as you can see in this diagram I'm talking about. Okay, and then we're going to have the iron making to make the iron. Then we're going to have the basic oxygen steel making to make the steel, and then we're going to have a different continuous casting processes, or we can continue to have the the same process can be done by using the scrap metal, and we can recycle it to make the iron again by refining and then continue with the casting later. We can simply do another processes, like we are going to take the finish or the casted parts, and we're going to make them as slab or pellets or blooms. We can simply make them hot rolling or cold rolling depending on the process we're going to have, and we can make them as a steel construction product, and this will be longer products, and we can make them as a flatter products like the plate, the sheets, and the tubes. So the iron making is extracted or will be initially processed before distribution to a steel mill according to its mineralogy. But the general is going to be concentrated and pelletized to improve the handling and the economics. In parallel, coke is going to be acquired through the extraction and processing of the coal by using the coke making. The iron ore pellets are then going to be fed into a blast furnace. Coke is going to be added to improve the source of the carbon as well as the reducing environment. The limestone is also added to assist with the removal of the impurities, forming what we know as the slag. So the key reactions are going to be first the production of the reducing gas, and this will be by adding the carbon plus the oxygen to have the CO2. The CO2 plus an excess of carbon or coke, we're going to have the 2 CO2, and this will be a reducing gas. The reduction of the iron ore is going to be by adding the iron oxides and two atoms of the iron oxide, what we know as the ore, plus three atoms of the coke or the carbon. We're going to have the iron plus three CO2s. So also we can have the FeO3 plus the 3 CO2, and this will give me 2 Fe plus 3 CO2. The output of the blast furnace is molten iron at about 1500 degrees. It's called a pig iron, and it's rich with the carbon and will be very brittle if applied as an engineering materials, hence require a further refining. So once again, the first iron we're going to have is going to be the pig iron, which is not going to be strong enough because have a high amount of the uh, carbon, and this will make it quite brittle material. The slag is also produced in the blast furnace. Slag is an accumulation of the impurities that have been separated from the iron from a way to form a waste product. So actually, if you saw any of the casting or casting video, you will find that actually there will be a some it looks like a dirt on the top layer of the molten metal, and this should be removed. Okay, we call this slag. So you know that the iron or the carbon or whatever the thing is, it's going to have some, for example, impurities coming from the sand that's during the extraction process. Okay, and this can be removed very easy. There are other methods for the reducing of the iron ore to iron, but the blast furnace are going to be the most common, and these are going to be referred as direct reduction processes. Now we go to the steel making. The carbon contents in the steel should be arranged from about 0.06% to 2% maximum. Less carbon content is considered to be an iron which is soft. More carbon content yields for the cast iron with extremely low ductility, so it's going to be more brittle. That's cast iron. These alloys are limited to casting as the only fabrication process. The cast iron cannot be rolled, cannot be forged most of the cases. So they're all going to be casted and machined. The carbon contents in the pig iron is about 4 to 5%. The pig iron may also contain other impurities. Oxygen is used to perform the refining of the pig iron. So the steel refining takes place in either a basic oxygen furnace or an electrical arc furnace. In modern steel mills, the output steel is going to be delivered to a continuous caster, which is going to produce a steel in slabs for a future forming as required, because this slab can be formed to a different shapes. It can be later rolled to be a sheets, or can be formed to be an eye beams, for example, or simply just making a different types of the slabs for the machining. Producing steel from recycled steel is produced in a mini mill, and due to the economics benefits of the mini mills are increasing the numbers, but tends to be focused on a single steel product. Specific is going to be structural sections. The steel shaping and the finishing processes, the hot finishing, will involve the fabrication of the steel into a shape whilst it's then going to be still hot, which about something like 600 degrees. Under the application of such stresses, the grains have a sufficient energy to recrystallize such that the internal stresses are going to be minimized or eliminated, and so the product doesn't become harder or more brittle as a result. Due to the high temperature, the imposed dimensional changes can be high because at high temperature usually is going to be expanded, while the cool down is going to be shrink, and this will cause the dimensional change to occur. The cold finishing involves the fabrication of the steel into shapes at room temperature. Well, actually, it's not going to be room temperature. Sometimes something like 100 degree, 150 degrees is going to be considered as a cold finishing. So unlike the hot finishing, the cold finishing can only impart small changes in dimensions. For example, about 10 to 20% of so multiple passes are going to be required in that case. Now, that's something very easy. When the highest changes can be occurred also in the hot finishing when you apply the stress, because what's happening is that we're reducing the hardness of that material when you impose the heat. So it's something like take it to high temperature, at certain stage is going to be melt. So the high temperature itself is going to make it soft, even below the melting temperature. Some like 0.6% or 0.5% of the melting temperature is going to be called the recrystallization temperature. That makes the material at very high ductile level and very high soft, and then we can shape it. In the cold finishing, because it's remain cold, so it's going to be harder to be shaped, and thus the maximum dimension change is going to be achieved something like 10 to 20%. So if I get to have a plate with 5 millimeter thickness, I want to roll it to 1 millimeter thickness, I may have to do it over 3 or 4 steps in the cold forming or the cold finishing, while in the hot finishing maybe 2 steps is going to be enough, and sometimes even 1. So, however, due to the inability for the grains to recrystallize, internal stresses accumulate and the steel becomes increasingly hard and brittle at the same time. So, usually the cold finishing sometimes required to have a heat treatment. So, this phenomena is called the work hardening. Such steel may be referred to be as a cold worked. So these are some of the processes as we mentioned earlier. That's what we're going to have in the case of the hot finishing or the hot work. You can see that the material at the hot temperature first is going to be passing through the rollers, and thus we're going to have the recrystallization to be occurred just after passing the roller. So not too much changes as before and after. Well, if you're going to do it during the cold finishing, you can see that the grain reduction size will occur. And thus we're going to have, once again, strong but brittle material. So we have some global considerations for the steel production. Um, the steel actually produced by over 50 nations around the world. Whilst the AISI or the ASTM designations are frequently going to be used to describe the steel product, it's important to consult a certificate of the analysis to confirm the expectation due a multinational nature of the steel supply. Some of the nations can produce steel from their domestic supply of iron ore, whilst the other rely on the iron ore from other nations. For example, most of the steel in Asia is derived from the iron from Australia. Supply chain logistics are subject to volatility as a result. An iron ore abundant resources, which can be consist about 5% of the earth crust. The steel making is very energy and CO2 intensive, and that's why actually many of the countries try to push away their steel manufacturing due to the what we call the environmental regulations. So in Australia, we still have some steel manufacturing exists. For example, if you go to Port Kimberley, you will find that there will be a steel working area where they actually collect the ore. You can see them in this area. Well, let me get my pointer here. So in this area, you can see that the ore is going to be first accumulated. It's come by train, and then it's going to be taken through the iron making and the steel making, and then the parts will be exposed. Some of the iron actually here is either shipped to the area, or is going to be only prepared for export. So this is the PHP still working in Kampla overview. Well, actually, there are some visits to the place where you can actually be taken around and see the process of the manufacturing. Now, the other topic is going to be the aluminium making. So I think that you hadn't seen the aluminium in as a raw material. That's how we are going to find the aluminium ore. So we start with the production of the aluminium. Aluminium can be replaced with steel in most of the instances that are not going to be highly structural. Aluminium is a lightweight, corrosion resistance, and superior conductor of the heat and electricity. Hence, the aluminium alloys are essential. So the aluminium is relatively new engineering materials, having only been commercially available since the 1940s. While the aluminium is more abundant than the iron, which is around 8% of the Earth's crust, it exists as a complex silicates that are going to be difficult to refine. So commercially, aluminium is obtained from the bauxite, which is a hydride from the alumina, or the Al2O3. Alumina is very hard with a very high melting temperature, which is about 2000 degrees. So the aluminium is produced by an electrochemical process where the bauxite is going to be dissolved in a molten corallite at 1750 centigrade. The resultant is going to be aluminium ions are going to be then reduced to aluminium, which melts and collects at the bottom of the cell. Okay, so the aluminum products can be simply classified or readily worked into a shapes, which can be called the rods or casts. So example include for the rod is going to be the foil, the sheet, the plate, the bars, the rod, the wire, tubes, channels, and structural shapes. For the cast, it's going to be all the common casting forms, including the investment casting of the aluminium. The aluminium alloys are also available in a wide range of the surface finishing. For example, is going to be anodized and etched as well. Aluminium alloys are also available in a wide range of the compositions and heat treatment, which combine to provide a broad spectrum of the applied performance. So you can see here about the timber designation we have for the aluminium. If we're going to have the F type, is going to be as fabricated, no special controls. With the W is going to be where the solution heat treated, which used only on alloys that naturally age harden. And we have the anneal type, where the rods alloy only, or the O types. The H type is going to be strain hardened, where it's going to be a cold work to increase the strength, or rod alloys only. We have the T type, which is thermally treated to produce the effects of the other than the F, O, or the H. So we have once again a global considerations for the aluminium making. The first thing is that China is the largest producer of aluminium in the world. The US has declined in aluminium production but remains the leading consumer of the aluminium, where using about 22% of the world output. The production of the aluminium is very energy intensive, that requires about 16 kilowatt per 1 kilogram of aluminium, which is actually too much. Consequently, the energy-rich nations such as those in the Middle East are expanding their contribution to the global aluminium supply, like Saudi Arabia. The use of the carbon electrodes and the carbon baths for the electrochemical processes of the aluminium will lead to the CO2 emissions, something like 4 kilograms of the CO2 emitted per every 1 kilogram of aluminium produced. Finally, the bauxite is abundant overall, but current aluminium producers rely only on imports. Aluminium, Australia is the major supplier of the bauxite and also produce some of the aluminium grades. Now we come into the copper production, and the copper has been used by the people since the ancient times, primarily due to the fact that this could be obtained in a near pure metallic form and was easily shaped or hardened depending upon the application. In modern times, the copper is used extensively for the electrical applications due to the high electrical conductivity, and also the copper is heavily used in the plumbing and is inherently resistant to the biological growth. The availability of the metallic copper has long been exhausted, and so the copper ores are now mined for the copper production. At a typical copper contents of 1.5% in the weight ton, much of the costs associated with the copper are due to the fact that it's associated with the refining process. The copper alloys are typically going to be 6 times the cost of the low carbon steel. The high purity copper with 99.9% is obtained from the copper sulfide ores via the follow processes. First, the concentration via flotations, methods of the crushed and the melt ores. Second, the roasting of the ore to change its mineralogy, but not cause the melting of the copper. And this will enable the concentration and later steps. The smelting, which involves the melting of the roasted ore in a controlled atmosphere. This will produce what we call the copper sulfide or the mate. This will enable the impurities such as the iron to be removed by the oxidation process. The molten copper mate is oxidized in a similar fashion to the BOF process for the steel making, and this will yield about 98 to 99% purity. The electrolytic refining increases the purity 99.9%, and this will involve the reducing moderate purity of the copper into a high purity copper plate at the cathode. Then the copper can then be melted off the cathode and consolidated. So there are many types of the copper and alloys, and confusing the vocabulary exists due to the uh, fact that many of thousands of years of their use. The main types are going to be first the brass, which alloy of the copper and the zinc, but also can include others such as the lead or the tin, with the lead brass or the tin and the tin brass are the two main types. The bronze. Bronze is an alloy of the copper and tin, but some of the tin contents can be less than that for the aluminum or the magnesium contents. The copper nickel, which alloy of the copper and the nickel at the same time. The nickel silvers, which is copper alloys with the nickel and zinc. The copper can be produced as a wrought or cast forms with many different varieties, such as the reflected above. The global concentrations for the copper production are first, the top producer of the copper are Chile, USA, Peru, and Australia. In 2000, China had the greatest demands for the copper products. The use of the lead-bearing copper alloys, like the leaded bronze, has begun to be banned due to the health consequences of the lead. The lead improved the emissionability of the copper alloys, and alternatives to the lead are being explored. Due to the bannings of the leaded copper alloys, there is an emerging declines in the supply of the copper bismuth alloys, such as the bismuth is a byproduct of the lead production. The overall copper supplies are adequately meeting the global demands and are expected to continue doing so for the foreseeable future. The concrete is the most widely used engineering materials in the world, used for the building, roads, dams, and extra. The concrete is a composite of the sand, aggregate, and the cement. The cement is a critical ingredient and forms a ceramics like a material that bends uh, everything together. So the prior to the innovations of the Portland cement, a machinery cement was used which based off the hydrations of the silica and required bricks and stones as an aggregate. The Portland cement is also based off the limestone, but it includes an addition of the clay, and when sets, the forms of the complex compounds like the CaO, the SiO2, the Al2O3, and the Fe2O3, and the MgO. The Portland cement does not require the bricks or stones for its strength and can be poured into a required shape and was set it resembles an artificial stones which is known as the concrete. Starting as a dry mix, the Portland cement reacts when water is going to be added and the process will start within a minutes actually, but continuous for several months. For maximum strength, the reaction should be kept wet as long as possible. So the clinker is a reactive component of the Portland cement and is responsible for the formation of the tobermorite gel upon dehydration. The clinker is a result of the heating of the limestone and the clay or shell to drive off the carbonate and leave the reactive quicklime. The clinker production takes place in a rotary uh, kiln and at high temperature. So the global concentration we have for the concrete is that 10 billion tons of the concrete are used annually worldwide. The China produces about 60% of the world's cements, followed by India, Vietnam, and the USA. The cement production accounts for about 8% of the worldwide CO2 emissions, and the CO2 is emitted during the decarbonizations of the limestones or the clinker production, and in the burnings of the fossil fuel to generate the heat for the process. The embedded energy of the concrete is about 1 to 1.5 megajoule per kilogram. And the high thermal mass of the concrete does support the design for the high thermal efficiency. Now we go into the glass. We start with the glass production. The glass is produced by heating of the raw materials sufficiently to form the melt, and then allowing that melt to solidify at a controlled rate. The most common commercial glass is going to be the soda lime silicate glass, silica glass, which is going to be obtained from the silica, soda ash, and the limestone. The glass can be formed into various shapes via the blowing methods, for example, the bottles, or the pressing methods like the dishes. The sheet glass for the window, however, is going to be produced via the float method, whereby the molten glass is going to be poured into a path of the molten tin and is slowly cooled by pulling the glass sheet over the path. This will achieve a very flat and smooth surface finish, and after being removed from the path sections, the glass sheet is going to be annealed to remove the stresses, and then it's going to be cut to the desired length for the further handling and finishing. This method is known as the Billington process and was developed back in the 1950s. The global concentration for the glass productions are China is the largest producer of the float glass at 13% of the total global export. Germany and the US are at the 10% and 7.1% respectively. About 80 million tons of the float glass is produced worldwide every year. 38% of the silica sand for the glass production comes from the Asia Pacific, with a significant environmental impact. The demand for the silica sand is also driven by the growing demands for the fiberglass materials and for the use in technology for example, like the device's screens or the solar panels. About 380 megaton of the silica sand were mined in 2022. 1 ton of the floating glass requires about 1000 kilowatt hour of the energy and produce about 500 kilograms of the CO2. So some of the important readings and the references are going to be once again the Ritwich and the Callister for the material science and the engineering chapter 13, and we have the Budinski and Budinski for the engineering materials 9th edition for the chapter 12, 18, and 19. And once again, thank you very much for your listening and see you in the class very soon.